Hey everybody, welcome to Real Time with Redpanda. This is episode 5. We're going to be talking more about the internals of Redpanda, sort of continuing our series on that stuff. And we're going to be talking specifically about the RPC communication system that Redpanda is using internally and how that's really pushing the performance envelope. So I'm excited to have that. I've got a regular guest here, Alex G, founder of Redpanda. Alex, thanks for joining us again here.
Alex, thanks for having me. It's always fun to be here, and we get to just nerd out on the quirkiest things. It's always a ton of fun to come and live draw the communications infrastructure.
Yeah, absolutely. I love it too. Before we do that, I do want to talk about some news and specifically congrats to you and to Redpanda generally for being named to the Tech Enterprise 30 list. Even got your picture up in Times Square. Look at that on the NASDAQ tower, Redpanda showing up there. So that's exciting. If people want to go check that out, pretty cool thing there. I know there were 900, 1,000 companies they were looking at there and chose 30 or 40 of those. So pretty exciting and congrats to you all at Redpanda.
Thank you. It's kind of fun to see that. Honestly, I never really thought we were going to be in NASDAQ.
Right.
2.5 years into the company. It's a ton of fun. What was missing is it's my picture, so I could send it to my mom. I've been trying to explain what we do for forever, and I texted mom. I was like, "Hey, mom, we're gonna be in Times Square," and she's like, "Okay, send me a picture." And then this was the 1 year where they don't include a picture of you, so she's still, anyways, she's excited, but it was just fun to have a picture.
Yeah. Well, in a couple of years, when you're ringing the bell at the New York Stock Exchange, you can get your picture up there then. So that's cool. Another thing I want to say, news for me at least, you can see I'm decked out in my brand new Redpanda swag that I've been wearing. Got that since our last show. So if you're interested in getting some of that swag, make sure you get connected with us. You can join the Redpanda Slack channel. So go to redpanda.com. Join the Slack community there and reach out to some folks, and we'll get you hooked up with swag if that's something that you're interested in. Last piece of housekeeping I want to do before we get started. In a week and a half on March 22nd, Redpanda is having a virtual workshop talking about WASM and Redpanda, how that's happening. So again, go to the redpanda.com website, check that out, sign up. Everyone that attends will get a copy of the WebAssembly, definitive guide from O'Reilly, which is a great resource. So if you're interested in looking at that, we'll do that. Without further ado, I want to get into our topic today because we got a lot to cover. We always run out of time. But today we're going to be talking about the internal communication of Redpanda, specifically the RPC system and the specific library that Alex and his team have built. So just to set it up a little bit, I'm more of like a web developer, application developer. I'm used to communicating with JSON APIs and things like that. In some certain circumstances, I might reach out for like gRPC if it's a very, for me at least, performance important one that way. But I know you all have been pushing the envelope even further than that. Can you set us up and tell us, how you think about RPC and what you've been doing at Redpanda?
Yeah, totally. Did you want to bring up the
let's do that. There we go.
So today we're going to talk about really kind of the nitty-gritty details of the communication infrastructure, and I think just to set the stage, this is the first time that I have a couple of just images that I copied around from decks over the last few years. If we'll use it if we need it, but I think it's kind of foundational to understand two things when building a system like Redpanda. And I actually think for most applications, your threading is probably the most significant decision, and when it comes to building an application. So even before we talk about gRPC and stuff, which is useful for everyone listening in, threading has deep implications into just about everything. Right? It gives the developer a sound framework for how to think about building the rest of the application. You can choose a thread per chord architecture, which is what we've built, where it gives the developer a sound concurrency model, right? It says that there can only be one thing executed at any one time. And parallelism is left as a runtime variable. And we talked about that, I think, in the first 2 or 3 episodes of Real Time with Redpanda. So that's really the most foundational decision. The next most important decision is your communication infrastructure. How are you going to talk to each other, right? So if you have 3 computers that you have to send data to, and remember that Redpanda, for those tuning in, it's effectively a data storage. It's a streaming engine. It's a storage engine designed from the ground up for streaming data. And so when you have a client that is trying to send data to Redpanda, how are you going to send that data to 3 computers, right? There's basically built-in complexity into that. And so this is the second most important decision. And often when you're dealing about that, you have a huge set of options and from JSON and HTTP to gRPC, which is protobuf encoded HTTP post messages, to Thrift, which is its own binary protocol with its own header format, and so on, and the list kind of goes on. Flood buffers is another really important example. There's a Apache Arrow is basically built as a collection of utilities around the serialization format of flood buffers. So when you're thinking about that, this becomes the next most important decision, because a great deal of complexity will come from these 2 decisions, or really like building blocks. This is really your ground truth to some extent. When it's nice.
And
but
can you,
I think, go ahead.
I was just going to say, we got a great question I want to get to in a second, but when you're talking about all these different options, what am I sort of deciding between? What are the factors on each side that I'm balancing, to choose one or the other?
Yeah, I think let's talk about that. So I think on one end you have flexibility, and then on the other end you have performance. And it's really a spectrum. And so you want, if you're an application developer, the most flexible thing you could do is JSON, right? This is really kind of at the end. And the reason JSON is this stringly typed language or format definition, there is a parser in every single language. JavaScript has a built-in, C++ has this thing called rapid JSON that was built in by Tencent as one example. There's compile time compilers. Scala has its own thing. TypeScript is obviously leverages the JavaScript. Ruby has its own thing. I think it's natively built into Ruby, and so on. And there's probably a million libraries, maybe a million is too many, but there are hundreds of libraries probably with that can give you this kind of flexibility. And so this is on one end. Now JSON is expensive to parse in terms of compute time and memory size. And then on the opposite end, you have kind of binary custom. So an example on something that shifts all the way to the left are trading messages. And so like when you go and you talk to a hedge fund or something like that, they literally send, I don't know, I'm gonna make this up, but like 4 bytes. And the first 2 bytes is a size, and then you start doing kind of like bit arithmetic. And so yeah, it's really fun. And so you literally introspect every bit, because latency for them is a big deal. And so they will bypass safety and security, right? Because if you have to offload to a kernel module or to hardware, or maybe it might be too slow, and you just might miss your entire opportunity to trade. I think on the far left, you're literally talking about from the time the wire comes in until the time you can actually make a decision, somewhere around 500 to 700 nanoseconds. So this is on the extreme end of custom things. It's like literally bit introspection of a very small payload, and you're doing millions of those per second. And on the far right, it's exactly the opposite. You have these very verbose, very memory inefficient format, but it's super flexible. And remember that most applications aren't really in the millions of messages per second. Like if you look at most microservices that people are building, even for relatively heavyweight things, a couple million is probably on the higher end, that we see. Most for the belly of the market, and really for most applications, you're talking about 10,000, maybe 1,000, maybe 500 per second. That's still relatively sizable workload, but that's just the order of magnitude at which people are operating. And so if you're thinking about building an application, I would always err on the side of flexibility, because it's easy to debug. You can dump it to your terminal. You could see it. You could cat it. You could, netcat this thing and send like a custom thing. You can use curl to get a payload and view it on Chrome. There's just, the ecosystem is so rich to do that. You can, if you're building an interactive application with your browser, just say, hey, curl this endpoint, like JSON post this thing, and then you just get to parse it and actually access the object in that notation. It's just really a pleasure to work with.
Easier. Yep.
Yeah.
So it's kind of like the trade-off, I would say, between like compiled and interpreted languages, maybe, like if you're just writing a script or something like that, the flexibility of Python and doing something and doing it quickly and iterating is nice. But if you have something that's more performance sensitive, now you reach for Go or Rust or C++ or C, whatever you want to do there. So sort of the same trade-offs there.
Yeah, or assembly in the case of some HFTs. Actually, hard. You program it into an FPGA and send the device to your network. But that's kind of on the extreme end. On the and so I think it's important to understand who owns the complexity, right? It's basically an argument for complexity and performance too, and it's a spectrum. And I think for specialized systems like Redpanda, let me give you another example where we made probably not common decision, which was to not use the page cache, the Linux kernel page cache, or to build our own memory allocator, or to build our own read-ahead strategies. We have a very specialized system, which is we're a storage system. We are not doing like GPU decoding or anything like that. We have a very specific task, and the task is, how do we give people safety with regards to data loss, and shoving the bytes to disk as fast as we can, and then retrieving them and returning them to them as fast as we can, in a way that is compatible with the Kafka API. And so that's really the job. And because it's a spectrum, we get to choose. So an example is for non-critical APIs, for the admin API, because it's about integrating with an ecosystem like curl and a bunch of things, we actually use JSON. So you can send the JSON object to this admin API. But that's not really what we consider the internal communication. That's just what we expose to the user in case they want to do admin operations, like move a partition from one computer to another. What we're going to talk about today is how do you get Redpanda nodes communicating with one another in a way that is as efficient as possible with this. And so I just want to highlight, I guess, the orders of magnitude of performance and why we chose to onboard complexity. And, does that make sense?
I love that. Yeah, I think that makes sense. Also, I want to highlight a question that we've gotten from a viewer, and I think it's related to what you're going to go into. And they said, "Hey, Alex, you built Smurf SMF, but I believe pronounced Smurf. Often build the fastest RPC in the West. So, how much of that was inspiration in developing Redpanda? Is that what you use in Redpanda? So, I think you're going to get into that with some of your slides, but."
Yeah. Well, I mean, perfect question. Let's see. I actually have so this is a Smurf. It's an open source framework. It's Apache 2. You could use it. We actually started using this in the beginning for Redpanda, and we basically run into flat buffer limitations, and so I'm going to talk about that. But for general RPC framework, there is a Go port. It has also a very cute mascot too. Not as cute as Redpanda, but like clearly you can see I did this myself, and then the Redpanda is a professional designer did it. Actually, multiple firms. Here's what's cool about Smurf. I took a ton of inspiration from a Smurf, and so what a Smurf did is it parse the flood buffers IDL. So an IDL, it's a definition language. I forgot what I stands for, but it's a meta language, and it looks like C structs or Java classes. You say like object, the name of your object, like object person, and person has age and name and address and job or whatever it is. And job may be a different struct or a different class that, the job may have an address and a title or whatever it is, right? And so it's a way to give users a way to represent the data that at some point has to get shipped over a byte array. Like that, right? That's how computers work. At some point, you can only send bits, and bits in aggregate are bytes, and like you have to take this abstract thing and shove it into a byte array, and so you can ship it over the network. It's just how it goes. And so that's really what flood buffers give you. Now, here's the cool thing: flood buffers exploits the fact that most computers around the world are little endian architecture. And so it says, well, why can't we pad? Let me hold that thought for a second. But why can't we pad? I'm going to finish that thought, and I just want to go back and draw it because it's really critical to the rest of the discussion. Is why can't we pad the white space so that when you reinterpret the cast on the remote computer, it's just a single assignment instruction. So let me hold that on a second. But it's heavily inspired. There are some limitations that I want to talk about today. And I want to bring up a couple of things here. So flood buffers, as compared with flood buffers and Smurf are very closely intertwined in that Smurf is the combination of C* and flood buffers. And, and then I wrote an IDL generator, a compiler, that parses the flood buffers file and generates C++ C* code in the same way that and others contributed the Go port and the Python port. It's pretty cool. And in the same way that Kappa Proto is or gRPC is there's this definition file, and something parses that file and generates a bunch of code for the target language. But I want to highlight a couple of things. Let me know if you have questions. Is on the performance.
And I just want to clarify one thing too, I think, for the users. So here we're talking about, flat buffers, protocol buffers, rapid JSON. Those are serialization libraries specifically. And then we also have RPC, which, handles the communication, right? Often using a specific serialization library.
Correct.
Correct? Okay.
Yeah. And you need both, right? Like what the RPC mechanism will do is it'll leverage the serialization library to turn it into a byte array. And then that's when the RPC comes in that it has to serialize, it has to actually send it through the TCP connection. It has to be, equivalent of like TCP open and send and flush and, deal with things like back pressure and idle timeouts and heartbeats and a bunch of, that's really where the communication combined both things give you a remote procedure call. But anyways, just to highlight on performance as to why we went with the binary protocol with Redpanda, is that with flood buffers, is obviously the answer is it has to be better than flat buffers. Obviously, we wouldn't do. Is if you look at JSON, rapid JSON, which is one of the best JSON libraries in the world, I think written by Tencent, if I'm not mistaken, is on JSON to do 1 million times serialization of a particular struct mapping. In flood buffers, it took him 10 minutes to do the same thing. In protobufs, the protobuf light version, it took about 3 minutes. And in flood buffers, it took about 3 seconds. And we're saying that we can even do better, right? And so this kind of order of magnitude things, if your job is to send data and make it as fast as possible, it's a huge difference. Like I can't literally go to a customer, I guess you could, and say like, I'm gonna take 10 minutes to process this 1 million requests. Like it doesn't make any sense. It's too, it takes too long to do that, right? Like our job is to be safe and be fast, and so I think that the right approach for us was really to onboard the complexity of building a custom serialization format. First of all, because our APIs we don't need that kind of flexibility. Our APIs are rather mature. We use Raft as a way of communicating, and like it's just a very stable API. There isn't a whole lot of things there, and so it's okay to pay the cost of performance there. So this should give you an example on I'll now bring up the serialization library for us. This should give you an example on kind of the spectrum of flexibility. You get schema evolution. You get it supports backward compatibility in that, like on the far right, because it's all runtime reflection to some extent. You say, hey, runtime, do you have a field with this name? And the runtime is either going to tell you yes or no, and it has a string, right? So think of it as a map. You say, like, is there an Alex Debrie field? And the answer is either yes, and if yes, you assign the value, and if not, you're like, okay, well, here's, like, I'm still going to keep it in the byte array, but I'm not going to do anything with it. And so that's super flexible. It's really easy to use and to evolve and so on. And then let's talk about kind of on our end where we think we lied is in Felix, who wrote Sista++, in fact, Felix just wrote the version 2 of our internal implementation, but he has a very similar thing here, and it was really, we took a ton of inspiration of our version 1, which is what we're going to talk about, and just like RPC is kind of like Emacs. It's just the art of infinite and iteration or improvement. It's just like all these little percentages matter. So if you even compare Sista with flood buffers, Sista is even faster than flood buffers. And we just compare how flood buffers compares with rapid JSON. It's like 10 minutes versus 3 seconds. And so Sista has some really interesting things. Our internal serialization is very similar to Sista, and Felix is the one that wrote the parsing and serialization library. Now let's talk about that. Let's go back and let's do the live drawing here, because this is pretty cool. Here, this is at the end of the day. By the way, remember this one slide. I'm gonna go back and actually draw a couple of things to understand where we lie in the spectrum. So for our particular payload, we have a small metadata, and then we have a really large blob, like binary large object. It's typically what it is. So payload, right? Like we have just some bag of bytes. And the interesting part is our metadata happens to have one particular property that makes flood buffers not a good fit, and that is very nested types and polymorphic types. And so with flood buffers, the way it works is let's say you have a struct A, and you have let's say int64 x, and then you have int a, you have y, then you have int a z. What actually happens behind the scenes is that the flood buffers IDL compiler says, hey, this is 8 bytes, and then the sum of this is 2 bytes. Well, sorry, something that's my left headphone. Okay, so this is 2 bytes. And so you're missing 6 bytes here. And so it's gonna literally inject an int16 at compile time, sorry, at code generation time. It's gonna insert an int16 and then another int8. Wait, no, so this is just a regular integer. So it's 4 and 2 bytes, sorry. It will inject an int16, and then, but I guess it starts with bigger types. And then let's say it inserts an int32. So that should give you the 6 missing bytes, so that the total alignment for this struct internally is actually 16 bytes. I'll explain why that's useful in a second. So this is 16 bytes. The reason is when you pad the structs here, first of all, this is actually how C works. It has to do with memory cache line accesses. But when you so that you don't get fragmented line accesses, it's basically how it works. And so the reason this is useful is because you have deterministic sizing and layout. The layout is particular. You could pick any layout, but determinism is the thing that's key here. Because you have a deterministic layout, then on the receiving end, let me create a new slide real quick. On the receiving end, you can say, hey, I have 16 bytes. I am going to simply cast. I'm going to have an A pointer to a little a, and I'm going to say reinterpret cast from a character array, whatever. I'm going to a person A, this pointer, this char pointer. It's kind of low level in C, or actually in C++, but in plain language, it says that you have a byte array that is 16 bytes. And what you're telling the compiler is treat the beginning of this address as though this was A star. So a pointer to a person. That's it. That's all you're telling the compiler. And you're relying on the fact that it's the same CPU architecture. And so you have now the same CPU architecture, and you have the exact same memory layout. And so this is the thing that flood buffers really exploits. And so the problem with this is that when you have deeply nested types, a lot of these layouts change dynamically at runtime. And you kind of have to then send, it makes the serialization protocol rather complex, because then your envelope format has to be dynamic, and you have to send a bunch of headers to understand how you're going to reinterpret cast those particular bytes. And what was more kind of frustrating from a developer perspective is not necessarily that, is that I wanted to do it efficiently. And by efficiently, I mean like, computationally efficiently, and in a user-friendly fashion. And so what you end up doing is that you end up wasting some memory, right? Because remember that there's a bunch of padding, and you always have to pad to the largest struct. Think of it as the union types or some type in some language, as opposed to the smallest type. And so that's how you always have to pad the buffers, because you have to, if you're saying, hey, memory manager, interpret the beginning address as though this was the same person, like it has to be the same layout on both computers. And so what we did is we invented our own that was a lot closer to Sista, but it was specialized. And so the specialized problem that I want to highlight here is that our metadata layer, where I put that? Let's see, our metadata layer is small. And so let me talk about that. So by and large, we have what graph leadership term we're on, right? And so like what offset we're going to be saving to disk on file, small things like what compression, just like very small things, but we might change the small things. An example is when we do broker assignment, it's a relatively nested thing. It has properties about the computer and a bunch of stuff. And I really just wanted to define it in C++. And so because we have a specialized problem, I can build the specialized solution. And so here's what's awesome about this is that even though, so we talked about how flood buffers is 3 seconds, is an order of magnitude faster than protobufs, and 2 orders of magnitude faster than JSON. And I can almost another order of magnitude faster, almost, not quite, on the tail latencies for our internal, even compared with flood buffers and a Smurf. And so if you can take any kind of takeaway from this library, is I wrote Smurf, and I also wrote the first internal version of the RPC. So at least I guess you can take programmer aptitude as and eliminate that as a variable, because he was the same bad programmer that wrote both. And so this would be I think a high fidelity implementation between both. And the takeaway from that is that I can almost get another order of magnitude from, and I can get almost another order of magnitude by building a specialized struct. And what I think is this is really the main takeaway of this thing. And so how we do that is let's dig deep into C++. Before I get deep into C++, any questions from the audience? This is live, and we can just I'm just going to talk about some more low-level bits about the code generation and the runtime type reflection, but I'm happy to take questions from the audience.
We just got a good one. It's not even one I'm going to be able to handle. So I can read it, but you're going to have to handle this one for sure, because this is deep in the C++. So flat buffers seem very interesting now. seems like you've significantly invested in these high performance data structures. Have you thought about memory fragmentation in STL containers? For instance, standard.map is staunchly discouraged, but associative vectors or flat maps are highly encouraged. We can't even fit the whole thing on there. So how do you think about that sort of problem?
This is a really good question, and it's pretty deep. So
I'd encourage you to apply to the Redpanda team. Number one,
yeah.
if you're on this level, come work for Redpanda. But anyway, go ahead.
Yeah, exactly. So let's talk about memory fragmentation. Actually, because Redpanda is this is a rat hole, but this is a live discussion. So let's get into it. So Redpanda is a third code architecture. So assume you have core 0, and then you have core 1. And for those of you that listen to this in the future, if you get to join, then you get to just talk about whatever you're interested in this, like flat buffers and memory management. So what happens is at runtime, we take the entire memory and assume for simplicity that you have 2 gigs of memory total in your system. And so we evenly split it. And so we ask lib hardware locale to introspect from like, your CPU IO into the memory bank. So it's like, hey, for what core, let's say core 0, and this is core 1, though they're vertically stacked, what memory bank belongs to that, and then we say, okay, this is the memory bank, and then I'm gonna lock it to this thing, and nobody can access this except core 0, and then we're only gonna talk about this. What happens here is we don't use virtual memory, and so I do. But first of all, I agree that stip map is not necessarily a good implementation, and we use Absol as the Google container library for the node map, which has some particular structures. This is okay. This is deep, so we're gonna do it. So what happens is you have one gigabyte, and so the token truth of flat containers and flat buffers is just one particular way of representing it across computers, but Absol flat hash map and flat hash set, it's the idea that you can represent an order container in a flat array. And the reason for that is that you get memory prefetch in. And so the idea is that, in particular with absolute flat hash map, is that you should be able to look up an address with, I think, two cache line misses. So we're getting deep here. So let's talk about why that's not always necessarily a good thing when you don't have virtual memory. And so everything is always a co-design, and nothing happens without a context. And so what happens when you have a flat buffer structure in an application that will always suffer from memory fragmentation because we don't use virtual memory. And so we have to be very careful when we use flat hash maps. And so we actually, for our use case, we didn't find flat hash maps to be very useful for large containers. And the reason is that the reallocation and the space is a percentage of the baseline allocation. So well, here we are. So assume that you have a reallocation library, like you have to grow the container. And so you have your container is, and it often, I think, is 1.75x growth or so is the one, at least on the Facebook, same as like Facebook has a flat hash map thing. I think it's called F14 is the name of the map or something like that. But the point is that you take this and then you add 75% growth for the next reallocation. And in the meantime, well, I guess I didn't draw this at proportion. So here. Okay, let's do that. 1 second. So assume that that's the baseline, and then you got 75%. This is new. So when you reach saturation, actually when you're about like 80% or 90%, you can define when you're going to reallocate. Then the library will reallocate a larger pool and add 75% space overhead. This is the problem when you have a system that doesn't rely on virtual memory. This is too expensive. I can't simply allow that. I only have 1 gig, and that's my world. And either the allocation succeed or the program crashes. There's no alternative. I don't use the virtual memory subsystem. And so it's true, to answer the question, this is just really deep, that StdMap is a bad container for most things, but it's also not. And so the tree map container is actually better in the Absol container set. But it's not necessarily a bad container in general for large pools of objects. So an example is when you're trying to map offsets. At some point, you have to allocate this memory. And what we do is that then, instead of using the generic StdMap allocation library, you could use something that is specialized that says, hey, have a, I think the standard calls it a std colony, which is like, can you have a smaller versions of these maps around, at least for metadata? And so the idea is that you have 16 bytes lookups for particular hash collisions. And then this allows you to jump to areas of memory. And so the idea is that your key will be at most 2 cache lines away from lookup from a cache line, excuse me, from hash set collision. And you will always incur or not always, a lot of times you will always incur a cache line miss to retrieve the value, but it allows you to understand what happens with the new memory allocation. And so this is not necessarily a bad thing, because we do also use flat hash maps only in the case where the memory and the metadata is small, like we're talking about in the hundreds of objects or less. But for large objects, when you're dealing with thousands of hundreds of thousands of objects, a node lookup, which is a heap allocation reference with a dense key structure for hash set collisions, is not a bad thing. I don't know if that answers your questions, or that also lost the other 50% of YouTubers that are going to sink into this.
That was awesome. I mean, I just love seeing people in their depth, like going deep. So, I mean, the big things I would say is number one, hey, make sure you're coming to future streams and asking these types of questions, because it's great to see Alex G or just whoever at Redpanda. Like the depth at Redpanda is really interesting. You're talking about Dennis on transactions. You're talking about Felix on his, working on Sista and the internal stuff at Redpanda. Like if you want to know about this stuff, make sure you're coming and asking these questions, because we can get that sort of stuff. You can also join the Slack channel and reach out to people there and do that, or again, come work at Redpanda and solve some of these cool problems. Just to bring it back a little bit, I want to go back, and you were showing earlier like the metadata and the actual data. Can you give me a sense of like how big those messages are in general, maybe even each of those, and then like how many messages are you sending between brokers or different instances per second? Is that I don't know if that's a relevant question or not.
Yeah. So first of all, the metadata is low. It's like single-digit kilobytes most of the time, and 2 kilobytes is an extreme. It's very small. And so typically the Kafka metadata is and we wrap the Kafka thing into our own thing internally. We basically translate the types because Kafka encodes things, a lot of things. Actually, Kafka has a really artisanal encoding mechanism in that some things are encoded in big endian, some things are encoded in var-in, some things are encoded in like different mechanics, and there's like bit fields in this thing. And so I feel that it was just, I don't know if you've seen cathedrals in Europe over time, and it feels like every layer was built by a totally different generation of programmers. A lot of the encoding serialization of Kafka feels like you're building a cathedral in Europe over like a century. It's, at least to me, reading the code, it feels that way. And so
was that hard for you? I get for Redpanda to like basically re-implement. You want to have the same front door, the same API to Kafka. Was that a lot of work to do that and staying on top of that?
Yeah, so we gave up, and what we did is that we only implement the front-end parser, and then we immediately translate it internally into a thing that makes sense to us, that is generic.
Yeah.
And then we always, so the programmer, if you come in and say you're writing code for us, you really are dealing with internal types all the time. Like it's very rare that a developer has to deal, like you have to deal with the semantics, that's different. But in terms of dealing with the types and the structure, that's all sort of handled already. So we wrote this parser, this Combinator library that will will actually co-generate the C++ parse Kafka into our internal types so that the programmer doesn't have to deal with that. And that's all generated at compile time. And so you literally take upstream JSON objects from the Kafka IDL definition, put it into a folder, and then you get types, and you just don't know how it happens. It's kind of, it's not magic. This is the thing that makes it happen. But we, we didn't carry the semantics all the way to disk because we could do better in some dimensions. We could sort of like look back, we're like, okay, this is where you're trying to go, so we're just going to do here, and as opposed to like rebuilding the evolution. So in terms of metadata, and I know we're coming up with, we always run out of time, so I do want to talk about two things: reflection and the structure bindings, and how we ended up building. Like, what are the semantics that the C++ developer gets over the other flat buffers or IDLs and so on. So in terms of metadata size, it's typically a kilobyte or so. And think about what we do is we send heartbeats to other computers, or we send control messages, but it's small. It's just deeply nested. It's like, it's very rich objects, but it's just, it's tiny. And so we didn't want to deal with the overhead of flat buffers for us. It didn't make any sense. And remember that we have a very specialized problem, is which storage engine that is designed to be the best storage engine for our streaming data, and then we just added a very thin shim that translates the Kafka API into an internal objects, and then from there on is basically just Raft and a C++ storage engine. Like, we could, imagine you could build a database if you really wanted to. Not that we're interested in it, but the point is that that's really kind of the architectures. I think people tend to see us like, oh, you re-implemented the thing. I was like, no, we didn't. We built a new storage engine, and then we added a translation so that we can make money as a business on kind of the Kafka API level. Let's see. I probably want to get a chance to talk about all of this, but let's talk about the most important thing, which is these two slides, 9 and 10, are really kind of the most important one. So yeah, why not? This thing right here, it's called the structure binding. The idea is that you can splat a pod, a plain data object, and so if a struct that has no constructor defined and is trivially copyable and trivially constructible. They're C++ things. It means it looks like this. There's no, everything is public. There's no special ways of building it. You can use the default constructors and the nested types and so on. If you have a struct that is like this, and all of the transitive closure dependencies are also that way. So that is, you can have a struct data, and then you can have another data pointer inside this struct data that, like, say you're trying to build a linked list. As long as then the transitive closure of types are pods, then are trivially constructible and trivially copyable, and you can do this splatting, this structure binding splatting. Then you can start to build semantics. And so what we do is we have, and so you can look at this from Sista.rocks. It's an MIT library, and Felix actually wrote the next version. And so what we do is we write a complicated function on the type traversal that we tell the type, hey, what is the size of your fields, of your first order fields? Like, what is the size of the primitive fields? And the result of that is going to be a number, like 1, 2, 3. In the case of the data object, right, like this thing has 2. It has X and Y. And so the arity of this data struct is going to be 2. Ultimately, what that allows the developer to do is to always operate in C++ and let the compiler generate the code at call site. And then we just let the linker do a lot more work in terms of like trying to deduplicate code and branches and a bunch of other stuff. But the point is that at call site, we generate the instructions for serializing this into a byte array. And from a developer perspective, you always are operating in C++. You never are operating in sort of in a different language. And so it's very convenient and actually super fast to develop a new service or a new endpoint or a new thing. because the core engine was in C++, it's, we kind of built it. And I'll walk over the last idea, and then we have to close it up because I can talk about this for about 10 years, is that what we're looking for is a DFS type traversal. And so assume that you have a tree of types. The last thing remaining for this thing to work is the deterministic traversal of types. And so at this example, let's say that you're trying to serialize this node. The arity of this node is 3. We're like, okay, 3. I'm going to then go back and take the left turn and ask this guy, it's like, hey, what is your arity? The arity of this thing is 1. The arity of this is 0 and 0. And so when it's arity 0, we don't recurse, we simply extract the value. So this would be like integers. And then because it's 1, we say like, okay, what is your arity here? And then this guy will give you the arity of 2. And it says like, okay, I'm going to recurse to the left. And so the arity here is 0 and the arity here, okay, before again, they're like, okay, 0. So now I can go back and return to this thing. And so this is where the serialization happens on the way back. On the way back up is when the actual, we're like, okay, you're an integer here, 4 bytes. And we use very similar, for the low-level bits, we use very similar techniques to flat buffers. And so this is kind of where I took some of the lessons learned from Smurf, and and Sista does something very similar. And so it's a combination of that. And then we recurse again. There's no more left nodes, and so the next closest left is not the leftmost, is the right. Is 2 on the left, or like I guess 1 from the left. Is we recurse here, and then we ask it, hey, what is your arity? The arity is going to be called 0, and so it serializes to bytes. And so now you have 1, you have 2 on the way back up, the order. Then you get 3 on the order, you get 4 on the order, and then you get 5, and then you get 6, right? Because these are arity 0. And so at the end, the way it'll look on an array, you will have 1, 2, 3, 4, 5, 6. Now that you have deterministic order, you can go back and so this would be a byte array, and assume that, I don't know, for simplicity, it's all 1 byte. Then you'll have like a 6-byte array that then you can go back and rehydrate it or copy it, or, and then we do specialized tricks for specialized types too. And so the point here that I'm trying to make is we have a specialized problem that at the end of the day, this is really the slide that should take away. Is with JSON, it takes something 10 minutes to do whatever the performance was. With protobuf, it would take you 3 minutes. With flat buffers, it would take you 3 seconds. And then we can almost get an order of magnitude better for nested types when we specialize it further for our particular problem domain. I think that's basically, we have to wrap it right here.
I love it. And I love that idea of specialized solutions for specialized problems. It ties into something we talked about, in episode 3, when we're talking about like the read path optimizations. And because the Kafka API has pretty predictable, or just Kafka usage generally has pretty predictable access patterns from reading, right? You're going to be reading sequentially generally, and going forward, you can do some of that prefetch optimization even from, a remote store like S3 or something like that. So same thing here, you have these specific problems, and it's worth putting in the time to make a specialized solution for that. I'm glad that you all are doing it, and then I get to benefit, as a Redpanda user. Exactly. And I don't have to worry about performance stuff as much. So anyway, thanks for doing that again. Just reminders for folks, again, join the Slack channel. I do want to sort of, let me show the Redpanda site real quick. Take yours off. Hey, if you want to join the Slack channel, this is a great community. Just go to the Redpanda site here, and you up in the top right corner, you can see the actual Slack channel. Go join there. You can get some swag. You can talk to people like Alex G or Dennis or Felix or whoever from the team if you want to go deep on this sort of stuff. Also, I mentioned that virtual workshop that's happening March 22nd, so about in a week and a half. Going to be on Wasm. You get a free Wasm book. So make sure you check that out, and then also just be watching for future episodes. We'll continue either on some more internals or maybe into some use cases and different things like that. So hit us up with what you want to be learning. But other than that, Alex, always a pleasure. Thank you for joining. Everyone out there, thanks for watching, and be sure to check out old videos in the series as well.
Thank you for hosting. See you guys in the next one. Bye, everyone.